Okay, I'm just looking through, browsing these homework assignments, and a lot of you have done a lot of work. That's very good. I'm a little surprised that most of the engineers don't own a ruler to draw graphs with. I don't know. Not what I expected. Some of them are very neat, but some of them, I don't know. I'd suggest, it's a no-brainer to maximise your marks. Make, presentable report. Sorry, I don't want to single anyone out. Make a presentable report. Okay? That means graph axes are drawn with a ruler, not freehand. Okay? If you're drawing a curve, it can be difficult, but that's why we work in pencil, so that we can get it right, erase it, get it right, okay? Use a computer, Excel, or invest in some graph paper, okay? One book is like 50 baht. It has like 80 pages in it. You can make a profit, sell a sheet to your colleagues. For 1 baht each, you make like 3/4 of a baht profit on every sheet of graph paper you sell. Okay, so look, quite seriously, pay some attention to the presentation of your work. You will ultimately get more grade points for it. Okay. This is quite heavy. Are there any more to come in? Anyone not yet submitted? Is anyone not going to submit today and needs an extension? No one? Good. Put those there. Right, nearly fell over. Okay, so, can you take your seats again? Okay, so, I'd like to restart. So this part here, if you saw me writing onto the board here, I was really doing this and then up to the back of the classroom just to see if you could read it from the back. I personally found that I can't even read that from halfway up the stairs, but you young guys at the back of the room assure me you can read it, which is a good thing. Let's see if I can untangle this. Okay, so it's all set out on here. Personally, I prefer a smaller classroom where I have a nice whiteboard and I can do these derivations myself. There's something a little unsatisfying about just clicking a button and having the result presented on the board. But nonetheless, here we have the reaction A plus 2B to give you AB2. The forwards reaction has rate constant, not an equilibrium constant. The forwards reaction has a rate constant, Kf, and the reverse reaction, Kr. It's going back to last week. So we can write the expression, well, we may be able to write the expression, the forward reaction, Kf times these concentrations, or whatever the expression as determined experimentally would have us believe, and we can write the equivalent reverse reaction rate as Kr times AB2. At equilibrium, this is the point we've been talking about from the beginning today, the forward and the reverse reaction rates are the same. If you remember those graphs, both of them had horizontal slopes. So rate forward equals rate reverse. So we can equate this expression with this expression, and there they are. These expressions contain constants, and they contain variables. I'm hoping you can tell me which is which. Okay, so if we collect the constants on the left, the variables on the right, we're going to get something like Kf divided by Kr equals to AB2 over AB squared. Yes? We're going to get Kf over Kr, and that of course is now equal to Kc, isn't it? And there's our product over the reactants. That's where the equilibrium expression, or the law of mass action, that's where it comes from. So Kc, well, all Kc is the ratio of the rate constants for the forwards and reverse reactions. Okay? And in fact, sometimes, when I do this topic, sometimes somebody will say to me, well, Adrian, if we can't include liquids and we can't include solids, what do we do for solid phase reactions, where all of the reactants are solids and all of the products are solids? How on earth do we determine what Kc is in that case? Because it would have no terms in it. And in fact, if we do that, then we can work out, we can go back to the kinetics for a solid phase reaction, and we can look at the forward and reverse reactions, use the rate constants to derive Kc. In other words, we do it in a slightly different way. Nonetheless, so that's where Kc comes from. The title of this section, Chemical Kinetics, that's our two rate constants, is related to chemical equilibrium, because the equilibrium constant is just the ratio of the forward and reverse rate constants. Is that clear-ish? Okay. Now, do you want to have a look? Okay. Now, we have another concept. This is remarkably useful. QC, I'm not going to use this very much. In fact, I'm not planning. I've got my own way, which I personally believe is a lot clearer. But here you can see the value, well, QC, I'll tell you just what it is in a minute. But this diagram shows the case where Kc is greater than QC. Here the two of them are equal, and here one is, QC is greater than Kc. That's implying what we're going to do is when we get QC valued, then we compare it to Kc to say, well, is it bigger or is it smaller? Okay. Now, Kc, as you know now, is the constant that describes the concentrations of reactants and products at equilibrium and at no other time. If it's not at equilibrium, then it's not Kc. QC, however, QC is the ratio of reactants and concentrations at any time, including equilibrium. So it could be right at the start, right at the end, 10 minutes into the reaction, or at equilibrium. So QC is derived in exactly the same way as Kc, using the same rules, products over reactant concentrations, but QC is the value at any time that we happen to consider. Okay? If QC is equal to Kc, then we know the system is at equilibrium. If QC is bigger than Kc, then that tells us something about which direction the reaction is going to move. So before I actually show you, for instance, we'll come to this side of the board, and in place of drawing big green and red blocks, I'm going to draw a line, okay, and in the middle of the line, I'm going to put Kc. Okay, now I've got a tick here, then one here, and one here. Here. If QC, I'll put it underneath. If QC, no, I'll put it over the top. If QC is here, then it's less than Kc, isn't it? If QC is less than Kc, what the reaction wants to become equilibrium. So the reaction will move to the right to regain equilibrium. If we have reactants becoming products, okay, when I say the reaction will move to the right, what I mean is reactants will convert into products. Okay, so if QC is less than Kc, the reaction will move to the right. If QC is much greater, or is greater than QC, then you can see the reaction will now move to the left. And what does that mean? That means products will decompose or do whatever it is they do and reform the reactants. The reaction will move left. If QC is equal to Kc, then the reaction is at equilibrium and there will be no further change, unless we shack it up somehow. Okay? So this is, I advise you to use this because this is incredibly quick and it's very easy to understand. Okay? You'll have a numerical value for Kc, you'll work out a numerical value for QC. Is QC bigger or smaller, or is it equal? If it's equal, the system won't change. If it's bigger, the reaction will move to the left. If it's smaller, the reaction will move to the right. Okay? So, that's the method. I can't remember if I came up with that myself or read it somewhere. Okay, so there we go. So what do we actually say here? The reaction quotient is calculating exactly the same way as when we calculate Kc. If QC is less than Kc, now, if you have this line diagram in your head, you do not have to memorize this information. That's the great thing about it. Just conjure up the line in your mind's eye and you can solve the problem by thinking instead of recalling. If QC is less than Kc, then the reaction QC must want to increase. It must want to move to the right, which is thankfully what it says. If Q equals Kc, it's already there, so it's not going to go anywhere. And if QC is greater than Kc, then it's going to want to get smaller. Okay? Remember, reactants over products. So if QC wants to get smaller, it's going to have to increase the product concentration, isn't it, to make itself bigger. Did I say that right? No, I said it completely wrong. Somebody put me right. Okay, so if QC is smaller than Kc, QC is products over reactants. If QC is smaller than Kc, then using our line, QC is here, reaction wants to move to the right. Is that the case here, where if we look at the equation? Well, if QC is smaller than Kc, then it could get bigger by increasing this or decreasing this. In other words, by converting reactants into products. And that's just what's going on here. If we move from left to right, we're converting reactants into products, and QC is becoming larger, greater magnitude, and approaching Kc from the left. Okay? Now, here's an example of how you might use this newfound knowledge, or this newfound wisdom of yours. At the start of a reaction, we have 0.249, three significant figures again, moles of nitrogen gas, 3.21 times 10 to the minus 2 moles of hydrogen gas, and 6.42 10 to the minus 4 moles of ammonia. Now, the only complicating factor here is this is not molarity, because this is in a 3.5 litre vessel. You know, and you may look at that, you know it should be simple to work out, but oh God, I have to think. Okay, it's really easy. To turn that into molar quantities, we just divide, where's my pointer? We just divide each of those concentrations, oh there it is, by 3.5. There it is. Okay, so that's the first thing. We're going to want to make them into molar quantities. So in your notebook, you should be writing down square brackets N2, 0.249. Make a little data table at the head of your problem. That's how I would do it. Write down the equation. Now, we know that Kc here is 1.2 whatevers. We have a a temperature, which if you needed to use it, you would need to convert to Kelvin, but you don't need to use it, so let's not worry about it. We want to know which way will the reaction proceed. We know that if we have this line, if we have Kc and we have Qc, we can do that. We do have Kc, so we've got to work out Qc. So write your expression for Qc for this equation, ammonia squared divided by nitrogen times hydrogen cubed. Substitute your molar data, so divide each of these by 3.5 litres. Okay, that will give you moles per litre, and calculate the value of Q. When you've got Q, you can put it onto this diagram here and work out if it's smaller than Kc or bigger than Kc. I can't remember which it is. I've got it written down here somewhere, because one day I'm going to come here and I won't be able to start the computer up and I'll be working from notes, and then you'll be in trouble. You'll have to put up with my spidery handwriting. But not today. Okay, so that's kind of your strategy. Generally, you're all engineering students, so I'm guessing you're getting a lot of problem-solving practice. Generally, you need to summarize your data at the head of the problem in some sort of structured form. Doing it in a table form would easily allow you to work out the unit concentrations. State your reaction or your equations. Decide on the variable that you need to find, which here is Qc, write an expression for it, and off you go. So here we are. What are we doing here? Oh, we're converting into our molar concentrations. Is that a question? No. Okay. What's he doing? Is there Spider-Man? There's no Spider-Man this week. I told my son, and he thought he was hilarious. Okay, so that's nice and straightforward. I don't think there's anything to worry about there. I'm going to stress to you once again about significant figures. All of these values are 3 significant figures. That's a great set of examples right there. Okay? If you were in doubt, you shouldn't be now. Even that is 3 significant figures. Your calculated values are going to be a little bit longer than that, but you don't want to lose a half a mark. You've got to sort them out, okay? Now, we've got our values, 1.83, 711. Let's have a look, 711, 1.83. So there they are. We've inserted them into the expression for Q. We've got a value of 0.611. Is that what you got, those of you who did the calculating? Now, put it on your line. Write in your value for Kc. I know you can do this in your head, but if you're setting out your working, that would count as your calculation. The great thing about writing this on your notebook or an extended problem is not just that you're showing working, but if it's a longer problem, you have to come back and retrace your steps. Then you've got some written note to say what you did then and there. So it's a great practice to not do things in your head, but to make notes as you proceed. That's a really great practice. 0.611. So here, Qc is down there. The diagram shows you very clearly that reaction will move to the right. If you need to justify that statement, then you can say, well, Qc is composed of products over reactants. If it moves to the right, then this number, if it gets bigger, this number is going to want to get smaller, this number is going to want to get bigger. Reactants are converted into products. Okay, reaction moves to the right. The net result, look at this answer. This is a bit more wordy than I would expect from most of you, but it's the sort of thing you should aim to produce in an explanation in a worked answer. What I've had in the past is people just drawing an arrow. You get a question that's taken me 2.5 hours to work out and do all the calculations to check it works in every phase, and then state and explain whether the reaction will move to the left or right. And I get part D, somebody will put an arrow like that, and that it does not count as an answer. I would give you a half a mark. out of 5, okay? So, take care. Give me proper sentences. That is a statement, but it doesn't even count as that. So please, help yourself, because the only person you're cheating is yourself, okay? You work hard all year. Let's not throw points away by saving a couple of seconds. My experience in exams is probably 80% of the room have left by the time the bell has gone anyway, so, okay. Okay, this is kind of the fun bit. Well, I say it's fun. This part here we use directly when we come on to acids and bases. What we're going to do is construct an ICE table. ICE, it stands for initial, change, and equilibrium. Okay, we're going to make a table. I'll show you how in just a moment. And then after you've done the table, there's a couple of little steps. We write, K equals products over reactants. We may know the value of K. The point is we want to find out what the change is. Which, when we make the ICE table, we're going to use a value, probably X. So we want to solve for X. And then when you know X, you can finish the problem off. So these probably don't mean much to you at the moment. We start by making an ICE table. And here's our reaction. Hi plus I2 to give us 2 hydrogen iodide. We got some data. It's 1 molar, so there's no worries there. Stainless steel flask, so we don't have to worry about expansion and stuff. We got 0.5 moles of hydrogen. Oh good, look, we got 0.5 moles of iodine. That's good because they're both the same. When they're both the same, there's a cute shortcut we can use, which I like because I hate arithmetic. So just notice they're the same. We've also got Kc value. Kc equals 54.3, and we want to find the equilibrium concentrations of hydrogen and iodine, because of course at the start we've got that and that, but they're going to convert to form some of this, which wasn't there at the start. So that starts at 0.5, it's going to end up being something less than 0.5. That's going to be less than 0.5. That's going to be something more than 0. We want to find out what those values are. Okay, this is what an ICE table looks like. I should have kind of set this out. When you create or construct an ICE table, what you do, you start by writing the balanced chemical equation. H2 plus, give yourself some room here to write the numbers, I2 HI, and there's 2 of them. They're all gases. I'm leaving, let's put the gas in. I'm a bit uncomfortable not putting it in. Okay, and then we can write ICE, that's initial state, change, and equilibrium. And in this problem, we've given, I know I'm recreating that, but I find it's easier to follow if you watch somebody creating it. So this was 0.5. The question tells us that. 0.500, 0.500. I'll just put a dash, 0, isn't it? Well, we'll assume it's 0. The change, some of this converts into that. So we don't know how much. We just say X. Okay, these are 1 to 1, so that is also X. But that's going to be 2X, isn't it? Okay. Now, at equilibrium, what we have is 0.500 minus X. Okay, the same here, 0.500 minus X. Okay, and this is just going to be 2X. So you can see, if we can work out what X is, we can work out all of the equilibrium concentrations. Okay. Now, we know K as well. We know K. What's the value of K? 54 something, wasn't it? Can't remember. 54.3, was it? Okay, well, okay. KC is equal to, well, I'm going to write the equilibrium expression. We've got HI squared over H2 I2. And instead of using these terms, we can substitute these algebraic terms in their place. Just go more than that. My hands are getting tired now. Yeah. Okay, so let's substitute our algebraic terms. Instead of hi squared, what we've got is 2x all squared, and hi we've got 0.500 minus x, and in fact that's the same, so I can square that term, and that equals, I do need to know what the value of k was, and it was written on the previous screen, so let's have a look. 54.3. Okay, so 54.3. Now this is a very easy example because there's a nice little shortcut we can do, because that term is squared, that term is squared, so if we just take the square root of both sides, we get the answer pretty well directly, don't we? Yeah. 2x over 0.500 minus x, I don't need the bracket anymore, equals root 54.3, which is 7 or something like that, isn't it? Okay? And then it's just a very straightforward, simple solution for x. So when the starting concentrations of this and this are the same, we have that nice little square root shortcut. I've left my pencil over there. Let's have a look. Oh, there it is. Yeah, that's the approach. Okay. So this is just what I've written over there. I hope it helps you to watch it being written out. But there's a permanent note for you. So the equilibrium constant is given by this expression, which after substituting algebraic terms, you may notice that we can take the square root of this and of this, and we get that. Solving for x, not particular rocket science there, we get 0.393. Again, 3 significant figures. Okay? Now, at this point, this is where 30% of you, no more, no less, 30% of you will forget to finish the problem. Okay? You will, I know you will. A couple of you are laughing because you know it's true, because that's not the answer. The question was to calculate the equilibrium concentrations. So hydrogen was 0.5 minus that, so was iodine. HI was twice that, wasn't it? Something like that. So here we are, 107, 0.107 and 0.786. That's the final answer. Okay? And I'm not just messing it up, okay? Students, I should put often forget this step. I could even say students usually forget this step, so be really careful. Okay? Okay, that's the mechanism. Now, the next example I've got, 14 point, yeah, it is the next example. The next example I've got is the same type of thing, but the solution to find x is a bit more involved because it's not just a simple square root. We have to use the quadratic solution equation. I think your appendix 4 in your book, in your textbook, gives you the quadratic solution approach. Minus b plus or minus the square root of b squared minus 4ac over 2a. You should know. Okay, so yeah, okay, so this is the new problem, and you need to work through this with me. Okay. I just want to check to see how much material I've still got to get through. We've done that, we've done that, we've done that. That's the one we're on. There's the quadratic Okay, just to let you know where we are, I'm going to run through this problem. Then we have Le Chatelier's principle to look at, which is an alternative approach to working out changes to a system to using Q. Personally, I think the reaction quotient method is great and it's unambiguous and easy to work out, but you'll see Le Chatelier's approach gives you a more qualitative method. For now, can you please set out the problem in your books, write out the equation, start off writing your ICE table and input the data that you're given. Okay, I'll give you a moment to do that. Which colour is better, yellow or white? White. Okay, thanks. I looked last week and I looked at the blue I was using and I couldn't even see it from the front row. It was so faint. Okay, so set up your ICE table. H2 plus I2 2HI. And as I suggested earlier, even if you can do these in your head, which sometimes you can, it's best to set them out. It's a great practice, but it does mean you can backtrack. Initial change equilibrium. Now what have we got? We've got some concentrations here. H2 is 0.00623, 0.00623. I2, where is it? It's the second one. 00414, 0.00414, and HI 00224. Is that right? 00224. 0.00224. Again, everything's three significant figures. Okay, so there we are, and we can put in, well, actually, can we put in minus x? See, the thing is, do we know this is the same as the previous reaction, so we know the value of Kc. Now, we also know that if QC is here, then the reaction will move to the right, and these terms will be minus x plus x. But if, when we work out for these concentrations, we see that actually QC is greater than Kc, then actually, when we do this algebra, that's going to be increasing, and so is that, and this is going to be decreasing, because the reaction will be going to the left. Do you understand that? It's a subtle point. So the first thing we have to do is to work out the value of QC to find out what's the direction the reaction is going to move. Okay? So what you need to do is use these values to work out the value for QC. Okay? And see, is QC bigger or smaller, or even equal? Because if it's equal, your work's done. You can go home, because it's at equilibrium already. So, QC is going to be equal to HI all squared over H2 concentration, I2 concentration, and that is 0.00224. Oh, I took too many. What, there? Okay. I couldn't see it properly. I'm trying to read it from over this side. Is that correct? You must have the eyes for Hawk to see that, because I couldn't possibly see it from over there. Okay, I think that's the correct expression. regardless, what's the value of QC now? Sorry, 1. QC. 19.45. Okay, so we know that, well, what was the value of Kc from the previous problem? Kc was at 54 point something. There we are. The value of Kc, because it was at the same temperature, 54.3. So 54 point whatever, 43. QC is down here. So reaction will go to the right, converting reactants into products. Now that just tells us if this is going to be a plus or a minus, and so on, all the way through. So we need a negative. That's going to decrease by an amount. That's going to decrease. This one is going to increase by 2x. Okay? Now we can write our expressions. Okay, and you can see that this time, unfortunately, our reactant concentrations are not all equal, so we can't just use the square root method. Sorry? Well spotted. Okay. 0.0224 plus 2x. Yes. Okay? Okay, well. Okay, so there are our equilibrium expressions. And now we know the direction of equilibrium, so we know these signs. We can write our expression for Kc, and so that I don't make any more typo mistakes. Now, I think I've run through this. Yeah, here we are. So we've compared QC to Kc, and then we've been able to work out the sign, minus and minus and plus, because it could have been the other way around. There we are, there's the QC expression. That's your 19.5 that you actually worked out for yourselves. And this is our conclusion based on that calculation. Then we can set up, which I think this is as far as we've got. And there's your comment there that it's plus 2x, well done. Okay. And that's as far as we've got. So where do we go next? What do we do now? We need to write out the equilibrium expression, okay, and then trying to solve that for x. So here's our equilibrium expression. We did it already, so I'm not worried about doing it on the board again. We can substitute our data, and it looks like we got a bit of a monster, okay? So I did this this morning. I do it every year before I do this, and I work through it, and it takes forever because I have to keep going backwards to correct my mistakes. And for that reason, we have PowerPoint, okay, where it's all done for you, and it looks like Agile never makes a mistake, but it's just not true. Now, I personally have huge problems going from that directly to this, okay? So, very briefly, because I know most of you, your mathematics and arithmetic skills are at this stage probably better practiced than mine are. I accept that. Nonetheless, there are going to be some among you who are looking at it and saying, huh? Where did that come? Okay. So what we've done is there's a squared expression there. So we've expanded the top expression. That's actually this. Okay. 0.224 squared times that plus and so on. That's this expression on the right. Then we've got this expression. Multiply that by that, that by that, this by that by that. Okay? And we come up with this expression. Now, I did this and it took me 2 pages before I actually did it without a mistake. There's my worked example. If you want to see it, come up and take a copy. You can see even this has mistakes on it. But I do work through these things to make sure I can do it on the board. Let's go back. Okay, so there's our expression. We've taken the denominator, moved it up here, so we got 54.3 times that expansion is equal to this expansion. That's what we've got. 54.3 times the expansion is equal to the numerator's expansion. Now, what we'll do is move everything to one side. We'll collect like terms, make it equal to 0, and after basically multiplying that out, collecting all the x squareds and the numerical terms into a final expression. If you're not sure about that, then you're going to have to work it through for yourselves. It's quite absorbing work, so it's not a boring job. It's just something you have to concentrate on to figure it. But it's a quadratic equation. We have an x squared term times an x term times a number, and we make it equal to 0. Then you can use this expression. Okay? Does everyone know how to use this expression? If you're not sure, look in Appendix 4 and it's set out for you right there. Okay? When you do this, you've got the plus and minus. You get 2 values here. One of them will always be ridiculous. The other one should be the right answer. Why is this one ridiculous? What's wrong with this value? Yeah, that's well done. We're very quick. That's greater than our initial concentrations combined. If we go back to the start and work out how much stuff we started with, this is an increase. Okay, so it can't be that one. That's your solution. Okay. And again, for x, we're not finished. The problem wants to know what were the concentrations. We have a value for x after crunching these numbers. If you've got a calculator, I had all sorts of problems. When I was, first of all, at college, actually doing an engineering course, and later a chemist doing a chemistry degree, I had all kinds of problems doing this. Calculators of the day, this was a long time ago, we just moved away from slide rules and log tables, I had a calculator that had plus, minus, multiply, divide, and 1 memory. That was it. Oh, and I think my next one could do like exponents and things, okay? And I was making all kinds of mistakes entering and calculating these. By the time I finished that college course, 7 years later, I had a calculator which could solve quadratics. You'd put in the coefficients A and B and C, and it would give you the possible answers. And nowadays, you can even just speak to your phone and it will tell you the answer. So time has moved on since like 1976, because that's how long ago it was. So there you are. Take care on these problems. Quiz the result. Work out which is, that's the bit when you're actually thinking. Work out which is the reasonable response. And don't stop there, because we needed these. So let's just go back and look at the ICE table. This is what we have to substitute. We've got these 3 expressions. Substitute your newfound value for x. Don't forget to multiply it by 2 there. And then set out your results. Okay? Nice little table. Don't just state the answer, show where you got it from. Include the units, use the correct number of significant figures, and you'll get full marks. Okay? Easy. I'm not going to be, in your exam, I promise you, you're not going to get a full-blown quadratic where you have to go through hundreds of calculations to show me you can do the problem, okay? You are going to have to work out x, and it might be a bit tricky, but I'm going to try not to give you the quadratic equation to do. It just takes too much time in a situation where you're very stressed already. Okay, provide a check. Okay, so if you use your calculated concentrations, you should arrive at Kc. If you don't, then you've made a mistake somewhere and you need to fix it. Okay? Okay. Oh, I'm just going to get a sip of water. I think we're going to finish about 15 or 20 minutes early. That's good news, isn't it? I'm just going to rest my voice for the moment. Now then. Okay, Le Chatelier's principle. Those of you who did chemistry at high school will probably have done Le Chatelier's. Did you do Q as well, the reaction quotient? No, it's what do you say, my Tamada? Is that right in time? Or is it Brocadit? I always get confused which to use. At high school, you tend to use Le Chatelier's principle, although I don't think it's not as easy. There's a lot more reasoning involved in Le Chatelier's, as you're going to see next. I personally prefer to use Q because it gives me much more quantifiable answers, and actually it's pretty easy. I thought we were on the screen. Sorry. So, Le Chatelier's. So Le Chatelier is not such a quantitative method. It doesn't usually give you numbers that you can compare, but it tells you the directions that a reaction will move in response to some stress. So if a reaction is already at equilibrium and you make a change to the system, you might add a reactant, remove a product, you might add some product, and these things will affect which direction the reaction moves in. Will it move left or right? As well as changing the concentrations, you can change the pressure if it's a gaseous mixture. You can change the pressure by changing the volume of a container. If you increase the volume, what happens to the pressure? It will fall, yes, of course it will. If you increase the volume, the pressure is going to drop. If you decrease the volume, the pressure is going to increase. Okay? Of course, adding more stuff or heating it up will change the pressure, but we're not concerned with those things. If we heat it up, we're going to be changing the value of K itself. If we add material to change the pressure, then we're more worried about the concentration change than the change in volume associated with it. In this case here, we can see by the green line, we have a situation where our hydrogen and nitrogen and ammonia were at an equilibrium, and what happened? It looks like somebody has added some ammonia to the system. Somebody's got their injector through a septum, they've put some ammonia or just poured some in, increased the ammonia concentration quite rapidly, and what's the system then done? The system has reacted to oppose that change. We've added ammonia, the system has then tried to remove the ammonia that we added. When we add the ammonia, it's no longer at equilibrium. It wants to regain the equilibrium. So it does that by decomposing ammonia And in doing so, it forms more hydrogen and it forms more nitrogen. Okay? Notice, it looks like we get more moles of hydrogen produced than we get moles of ammonia produced. Why is that? Why do we get more hydrogen than we get ammonia? Well, if you remember the balance of chemical equation, 3 hydrogens reacted with every 1 ammonia. So this black line should be 3 times greater compared to this red line, shouldn't it? Okay. So, the system, we've made a change, and this is Le Chatelier's principle in a nutshell, that a system at equilibrium, we've made a change, or in Le Chatelier's words, we've stressed the system. Well, he probably didn't say it like that because he was French and he would have had to say it in French. But the system has been stressed. The system then reacts in a way that opposes that stress. And it's done that, in this case, by shifting in the reverse direction to decompose or to remove the added ammonia so that it can regain an equilibrium. Can you see here we have equilibrium, but here as well, at the end of the reaction, we have another equilibrium. It has regained equilibrium, albeit at different concentrations. Okay? But the equilibrium constant will be exactly the same. Kc, if you use these values, will be the same as Kc for these values, although the actual concentrations are different. And we got some time in unstated units there, so I'm not sure of the point of putting the 60. Oh, that's the slide number. It's not a time, it's the slide number. I think there are 72 slides on this. Most of the rest of the ones I think are working out ones. So there we are. That's what I just said. We have a system at equilibrium. Apply an external stress, and the system opposes that stress in any way it can. We can change the concentration, as we've showed here, of a reactant or a product. And there we are. There's our system. We can add or remove these. We can add or remove this. When you're making ammonia industrially, what they tend to do is remove the ammonia as it forms. That means the system can never actually reach equilibrium. It is always being shifted towards the product. If that comes there, equilibrium moves to the right. So if you remove that as it forms, the system is always out. Q is always less than K, and the system will always be moving to the right, making you more money. In this case, this example, we've added ammonia there, and the system shifts to the left to remove that stress. By shifting to the left, it removes the ammonia. Okay? Are you okay with that for me to move on? Yep, okay. They're going, please move on, Adrian, please move on. Okay, so here we are. There's a general equation. We had this equation just now. Now we've got the AABB type of equation. So this is going to be a little summary. See if you can follow them through to work out what's going to happen. If we increase the concentration of the products, is the reaction going to move to the left or to the right? Which way is that? To the left. It's going to go out the door. Okay. Okay, oh, you're pointing on this. Okay, so if we increase the concentration here, it will shift it to the left. Okay, well done. Let's try another one. If we decrease the concentration of the products, what's going to happen? The system's going to replace it, isn't it? So it's going to shift to the right. Okay? This is a case where you'll be thinking of arrows in your head or using your thumbs or whatever. If we increase the concentration of the reactants, what's going to happen then? We've given a high concentration of the reactants. It's going to shift to the right, isn't it? Okay, to remove that stress. If we decrease the concentration of the reactants, I know you can work it out by looking here, but try to think it through. That's right, I see you doing it. So we decrease this, then the reaction will want to replace the removed substance, so it's going to have to shift to the left. Okay? You can do the same analysis in terms of what Q does. I'll just do one of them. I'll do this one. Okay? For Q, if we decrease the concentration of products, then Q is going to get smaller, isn't it? If it gets smaller, it's going to move to the right to grow again, become K, and it's the same end result. Okay? So you should be able to interpret this in terms of Q, or in terms of your Chatelier's, where you're saying, well, let's just undo what was just done to the reaction. So here's an example for you. You're given the same reaction. It's getting a bit boring now, isn't it? Okay, we've got Kc value, and we've got our equilibrium concentrations. If we add ammonia to the mixture, so that's the case given in that graph just now, the new concentration of ammonia is 3.65. Use Le Chatelier's principle to say what direction will the reaction move, left or right. Okay? So for part A, you don't actually need all the numbers. For part A, we know this system's at equilibrium, but we add some more ammonia. What's going to happen? Which direction? If we add ammonia, the system will want to undo that stress. That's right, it'll move left. Good. Okay, now part B. Calculate the Q value and compare its value to K. So, what's Q? Q is this term squared divided by that and divided by that term cubed. Substitute your data, 1, 2, and 3. Okay, you don't need that one. Okay, and come up with a value for QC. While you're doing that, I'll write it on the board over here. So Q is going to be equal to ammonia, concentration all squared, N2 concentration times H2 all cubed. And we want to substitute the data into that. So the Q value is going to be our new value, 3.65. You should be writing this out for yourself. One great way to learn it is to write these worked examples out. Now I'm looking for the N2 concentration, 0.683 times whatever the hydrogen concentration is, 8.8. Right? Okay, that's what it says. 8.80 cubed. Oh, okay, so it's divided into. And that comes to, I have no idea, what does that come to? About 3.65.
Divided by 0.83 times 8.8 cubed.
Which is?
28.26 times 10 to the power of -3.
Okay. Thank you. 28 point something times 10 to the -3, yes? I'll just call it 28 because I didn't hear what the rest of it was. Okay, so we have a value that's probably close enough to say that if K was equal to, what was K?
2.37.
What was it? 2.37? Oh, 237, okay. 2.37 times 10 to the -3. And That's 28 times 10 to the minus 3, was it? So that's going to be Q. If that calculation is correct, then Q is much bigger than K, and the reaction will move to the left, converting products into reactants. These meanderings do, of course, depend on you getting the calculation right. That is a problem with QC, of course. Okay, so that's your strategy. If you find that you want to go over this again, I'll stress to you that, or remind you, you do have this online now. Oh, there you go. So ammonia is going to shift to the left. There's our value. Oh, it's 2.86. Oh yeah, you're right, because we put 28. When you give these numbers, one more little pointer. I think the reason this looks a bit odd to me, let's put the 6. Just as a pointer, that is not scientific notation. Okay, I know you got it, and thanks for giving me the answer. But remember everyone, sign notation requires that the decimal point is in this position. 8, 6 times 10 to the minus 2. Okay? I couldn't quite figure out what was wrong with the number, and it was because it was 28 point something. Okay, so there we are. The value using our line system is bigger, so the net reaction will move to the left until Q is equal to Kc. Okay. Please look at this explanation at the end. Okay, you don't have to get it word perfect, but when I ask you to explain what direction a reaction will move, I do expect you to say what the effect will be. Look, this is saying what will happen, and this is saying why it happens. Okay, do try to give a complete answer. It doesn't have to be that answer. There's probably a dozen different things you could say. You could show you're working using that line structure. That will certainly tell you what the correct answer is. I don't think I've made a mistake using that method yet. Okay, so there's that picture once again. And perhaps now when you look at this, you understand what's going on in this picture a little more clearly than when you first saw it. An increase here, the system then removes it, and this stuff is converted to make more hydrogen and nitrogen gas. Okay. When I'm watching a PowerPoint, I always find it a little bit jarring when the presenter just changes it to the next picture. And it takes me by shock here sometimes. I can't, unless I look at the screen, I can't really remember what's coming up next. And, oh yeah, okay, so we just looked at concentration. Now we'll look at what happens. Volume and pressure, obviously, are very closely associated, inversely proportional. Increase one, you'll be decreasing the other one. In this reaction, we've got a gaseous reaction. We have 2 moles of gas on the left, we've got 1 on the right. So, if we increase the pressure, what will the system want to do? It will want to oppose our change, yes? If we increase the pressure, the system is going to want to decrease the pressure. It can do that by shifting to the direction with fewer moles of gas. See, if you've got 2 moles of gas here, they're going to try to take up more space than this if it was all C, yes? If you remember your laws of partial pressure and so on. So, if we increase the pressure, the reaction is going to want to move to the side with fewer moles of gas. In this example, the reaction will shift to the right to decrease the pressure. It will convert 2 moles of gas to 1 mole, okay, which would take up less volume. In a fixed volume, it will produce lower pressure. Okay, so that's the reasoning. For this example, you would need to say, does it shift left or right? Which way does it go? It goes right, doesn't it? If we decrease the pressure, conversely, then the system will try to oppose your change. It will try to increase the pressure again, and it can do that in this example by shifting left toward the side with the most moles of gas. Okay? Okay, you may want to write these down, but certainly I don't think you need to write these down. You need to write these and ask yourself what will happen. Make sure you work it out. Don't just rely on my telling you. If you increase the volume, what's going to happen now? If it's in a steel container, it cannot decrease the volume. If you increase the volume, what will that do to the pressure? Yeah, if I increase the volume, it's going to decrease the pressure. So the equation is going to shift. It's going to try and re-increase the pressure, isn't it? We have a pressure, increase the volume, the pressure drops. The system will try to replace that missing pressure. It will move to the side with the most moles of gas. Okay? I'm going to get one of these wrong one of these days. Okay? And if we decrease the volume, again, the reaction can't usually change the volume of the flask unless it's alien blood and it can burn through the vessel. Okay? But the reaction can't change the volume. Decreasing the volume is going to increase the pressure. The reaction can try and decrease the pressure by moving left or right. Yeah, it's going to move to the right, isn't it? To the side with the fewest moles of gas. Okay? Now, I'm not sure. Let's have a look. Okay, now, there's something I didn't put a note on here. If you have a heterogeneous equilibrium, you might have a solid, you might have a liquid, aqueous solution. However, when we change the pressure, the change in volume of gas is huge. If you change the pressure on a liquid or a solid, then there's zero or absolutely negligible change in the volume of the others. So, if you have a heterogeneous system, we only consider the moles of gas. We don't worry about the moles of aqueous media. We don't consider liquids or gases. They're not affected by pressure changes at all for any normal laboratory conditions. I'm not saying you're never going to be a physicist working on Mars, where perhaps such things might make a difference, but in our labs it won't make any difference. Okay, so considering these systems, we've got a solid and a gas and a solid and a gas. Okay, we're only going to need to look at the gases. We've got a gas and two gases on this side, and so on. Predict the direction of the reaction in each case, A and B and C, if we increase the pressure by decreasing the volume on the system at constant temperature. Okay? If you're on a bicycle and you've ever pumped a tyre up, you'll know that increasing the pressure will increase the temperature, but we're considering that to not happen. Okay, so predict the direction of A if we increase the pressure. How would we tackle that problem? If we increase the pressure, it's going to want to move toward the side with the fewest moles of gas, so it can decrease the pressure again. So look at A, we've got 3 on the left, 2 on the right. You can ignore the solids. If we increase the pressure, will it move left or right? Yes. What about this one? Left or right? Left, yes. I hope. Yes. And this one? No, it's not going to move, is it? Because we've got 2 on the left and 2 on the right. It's already at equilibrium. It's not going to make a pennyworth of difference. Okay. Okay, I think we've got... Oh, there is a little discussion here. Okay, this is your strategy. Something I haven't mentioned, but PV is proportional to N. Okay, but there's something else I want to write down, which I think I'm going to have to change the slideshow to include it. Okay, so from the ideal gas equation, BV is nRT. Okay, even if it's not an ideal gas, the general trend is going to be the same. If I bring the V over this side, V equals N over V RT, then number of moles over volume is just moles per litre, isn't it? It's just molarity. Okay, which means that P, as well as being proportional to N, P is proportional to the number of, to the concentration, to the moles per litre, to the molarity. Okay, just point that out because you can actually equate it. It can be quite useful to realise that you have that a proof of that relationship. Okay. So while P is proportional to N, it's also proportional to N over V, which is molarity, or molar concentration. Depending, you may not be using litres. Oh look, there's a, look, I wondered where it went. Look, you see my little, I lost it. I was using this, and I was sure there was a proportionality symbol written in here. And there it is, it's hiding above the M. Damn Microsoft. Okay, this is the reasoning to A and B and C, which you didn't seem to have any problem with. There's a check. Okay, well. Okay, now I spent some time trying to remove all these copyright notices. You know, it's quite reasonable of McGraw-Hill to put a copyright notice on their images, but at the top and the bottom, I don't know. I started doing it and it just got too difficult, so. What do we got here? Well, I think, as I recall, and I've actually seen this gas, this is a mixture of N2O4 and NO2. As I recall, the lighter gas, well, hang on, let me think. NO2, I believe, is a brown gas. N2O4, I believe, is a clear gas, transparent. So this is actually a mixture of the two. This one contains more NO2 than this one does. Okay, so there we go. So what we've got here is a mixture. Here, it's an equilibrium mixture. Here, then, but one of these two has been heated up, which has caused a shift from this form to the other form. It shifted the NO2 into the N2O4. We can change the temperature, but the change occurs by a slightly different mechanism. Now, I'm going to consult my notes because I actually considered an alternative way to present this from what the slides do. Concentration, pressure, temperature. Yeah, okay. And we're bang on target. I think we're going to finish a few minutes early. Okay, so this reaction, I notice it hasn't actually stated the reaction. So I'm going to give you this reaction, N2O4. You know it already, NO2, and there's two of them. Now, just consider, this cropped up last week. Which is the exothermic and which is the endothermic direction? Here, N2O4, that might be N2O4. To shift it to the right, we've got to break that bond, haven't we? That's going to require energy. Okay, do you remember from last week? So that to shift to there, this is going to be endothermic direction. This is going to be the exothermic direction. This is going to have a positive value on delta H. Yes? Oh, I thought somebody called my name. Okay. Okay, more colloquially, this, if it moves to the left, it's going to get hot. If it moves to the right, it's going to get cold. Okay, so there's a number of different ways to visualize what that reaction's doing in terms of energy, all because this bond is broken or reformed when it moves back that way. When it reforms, it's going to release energy. Okay, now, if we increase the temperature for an exothermic reaction, so that's endothermic, let's make it exothermic. Okay, so A plus B, A, B, okay? So this is an exothermic reaction. This side generates heat, this side absorbs heat energy, so it feels cold. Now, we're looking here, exothermic reaction. What happens when we increase the temperature? By Le Chatelier's, the system will try to oppose that stress. So the system will try to decrease the temperature. Okay? Now, it does it differently to pressure and concentration. What a change in temperature does, it actually changes the value of K. Okay? So, for an exothermic reaction, K will decrease. Why does that happen? Here's our reactants, here's our products. K is products over reactants. If it's an exothermic reaction and we increase the temperature, it will want to move to the left, forming more reactants, decreasing this. This one gets bigger. What happens to K? Does it get bigger or smaller? If the reaction moves to the left, it will favour reactants over products. It will get smaller, won't it? This number gets bigger, this one gets smaller. So K will decrease. Oh yeah, I did get that right. I thought I got it wrong. Okay? So for an exothermic reaction, think of this. For an exothermic reaction, it will go in the reverse direction, favouring reactants, so K will decrease. For an endothermic reaction, let's look at this one. For an endothermic reaction, if we increase the temperature, the reaction will try to cool itself down. It will move in the forwards direction. If it does that, it will favour products over reactants. K will increase. If we heat up an endothermic reaction, K will increase. Okay? Now, can you explain what's going to happen if we decrease the temperature for an exothermic reaction? See if you can work it out, yeah? Well, it would be the other way around, but what I'd like you to do is to work it out from using this, okay? Because that's, Okay, so what we need now, what have we got? For an exothermic reaction, that's this one. If we decrease the temperature, in this one, the reaction will try to increase the temperature. It will do that by shifting right, and it will shift right because it changes favouring products. So K will increase, okay? And let's just check we're right. K increases. Now, for an endothermic reaction, and now we'll look at the N2O4 reaction. If we decrease the temperature, then it will want to move in the exothermic direction. It will move to the left, favouring reactants over products. K will decrease. There you go, okay? So if you can, your choice is to kind of memorise that table, which means as soon as you've had your test, your exam, you can forget it. Or you can learn this process of working it out, which is probably, developmentally, that's probably a much better approach. There's a little equation here. Okay, as we worked out that delta H is positive, we did the same thing last week actually, by reasoning that this required a bond cleavage Okay? And as I said, these two pictures, this is the equilibrium state, but when it moves to the right, it forms more NO2 than there was previously, and NO2 is a dark brown gas, while N2O4 is a clear gas like nitrogen, so we form the dark colour as the equation shifts to the right. If it moves the other way, then it will become paler and paler until there was nothing at all. This stuff happens actually, if any of you live in a high-rise condo, like the 20th floor, and you can see the Bangkok horizon, you can actually, on a hot day, Songkran's a good time, on a hot day, 80% of the atmosphere is nitrogen. It's all getting sucked up into car exhausts and coming out as nitrogen oxides. Now, at the end of the day, most of the nitrogen oxide exists as NO2 or something very close to it. Okay? At the end of the day, we have quite a lot of this stuff in the atmosphere. And if you look at the horizon over almost any city, and Bangkok is no different, you can see this kind of haze, a faint brown haze across the city. If you're really observant, you'll see that it makes it about halfway up some of these tower blocks. You can't see it close up, but you can if you can see the horizon. If you look in the morning, it's not there, but it's there at the end of the day, kind of rush hour. And the reason for that is all of that NO2, which is there at the end of the day, when the sun goes down, it's going to start rejoining up. When the sun goes down, it starts rejoining up with the N2O4, and by morning again, most of the NO2 is converted back to this. So you can't see it in the morning because it's gone. And then during the day, the concentration will gradually shift, or the equilibrium will gradually shift from there to there, and then the colour can come back in the evening. Okay. That's not supposed to happen. Okay, now, you see this very informative picture. Now, McGraw-Hill have given me their copyright notice, but there is there's no image. Okay, so I'll just tell you about catalysts. You can just take some notes on this one, because what a catalyst does is it will speed up a chemical reaction, but it will not affect, it will affect the forward and reverse reactions to exactly the same extent. So it speed up the forwards reaction, it will speed up the reverse reaction. Overall, there's absolutely no effect on the equilibrium position. Okay? A catalyst has no effect on the position of equilibrium. Now, it does speed up a reaction, and the way that it does that is by reducing the activation energy. I mentioned this last week, and that was an exothermic reaction where this scale is the energy. There's the reaction coordinate. There's the activation energy E sub A. These are your reactants, here are your products. And that might be a fairly slow reaction. If I add a catalyst to it, it provides an alternative mechanism for the reaction to proceed. And the new mechanism will have a much smaller activation energy. Remember, activation energy is this distance here, and the new activation energy is just this distance. Okay? So the reaction of the forward reaction or the reverse reaction, they're both affected equally. Okay? The catalyst does not affect the relative ratios of product and reactant. However, if you do not yet have equilibrium, what a catalyst will do is allow you to reach equilibrium much more quickly. Okay? Thousands of times more quickly. If you have a reaction like the reaction of ammonia and hydrogen gas, then without a catalyst, very high activation energy, it might take you 3 weeks to get an acceptable yield. With an ion catalyst, it might take you 3 minutes. Okay, so it does, if you're allowed to reach equilibrium. So the catalyst speeds up the rate that you attain equilibrium, but it does not actually affect the equilibrium position. Okay, that's your key notes for catalysis. If you read in your book on catalysis, it's only a half a page. Okay, so feel free to have a look, find those missing pictures. Does not change K, only temperature change. Shh, we're nearly finished. Oh, you all shut up, that's the first. Okay, it doesn't affect K, only temperature affects K. It does not shift the position of equilibrium, but it does reach the equilibrium more quickly. Okay? Oh, here's my diagram. There's the catalyzed reaction on the left. There's the uncatalyzed reaction on the right. This one will proceed more quickly. That's why it is hidden, because it was a reveal. Okay, I should put equally on the other side there. If I wrote equally on the end there, that would tell us what it is we wanted to know. Okay, so they're the key notes. And here's a summary of the Le Chatelier stuff. The thing about Le Chateliers is not difficult, but there's a lot of reasoning step by step. If you want to become proficient with Le Chateliers, you just have to look at the end of chapter problems and practice them. Okay, remember, they might be equal. That's right, you said yes. Okay, just have a look at the results there, okay? We'll move on to that example. I think this is the last one. Yes, this is the last one. Okay, it's number 13. What have we got? Okay, so for this equilibrium, if we heat the reaction, what's going to happen to the equilibrium? Is it endothermic or exothermic? Well, delta H is telling us it's an endothermic reaction. If we heat this reaction, it's going to want to cool itself down, isn't it? It's going to shift right. If it shifts right, what's happened is products are favoured, so K has gone up or down. K has increased, isn't it? Yes? I think I said that right. So think about in terms of products over reactants. If we heat it, it's going to want to move into the endothermic reaction to cool itself down. If it moves in the endothermic direction, it's going to form more product. K is product over reactant, so K is going to get bigger. Yes? It's going to shift right. If we remove N2O4 from the reaction mixture, what's going to happen to the equilibrium? Chatelier will tell you that the system will oppose your change. It's going to want to replace N2F4. So equilibrium should shift to the left. If we decrease the pressure, what's going to happen? Left or right, or no change? If we decrease the pressure, it's going to want to oppose the change. It's going to want to move to the side with the greatest number of moles of substance to replace the pressure. So it's going to want to move to the right. If we add a catalyst, what's going to happen to the equilibrium? Nothing. Okay? Unless it's not yet at equilibrium, in which case it will attain equilibrium more quickly. Okay, so they're the problems. You can look at the PowerPoint. There's the strategy for each one. Here's your solutions for A and B at the bottom there. Oh, this comment, I don't want to go through this. If you're double thinking some of the points that happen this comment kind of explains something that I think you may be asking yourself. So you can have a read of that yourself. And there's the solution to part C. And there's your D. What a catalyst does is increase the rate of a reaction. If the system is not at equilibrium, it will reach the equilibrium more quickly. If the system is already at equilibrium, then there will not be any effect. Here, I'm not going to go through this. I did last year, but I'm not going to go through this. This is a case study at the end of the chapter. I found it was quite an interesting couple of paragraphs. If you're interested, read it. But it basically responds as the oxygen is depleted high up a mountain. If you lived in Tibet, for example, how does your body respond to the lower oxygen? Okay. Okay. So if you're interested in that example, just have a read. It's a couple right at the end of the chapter. Okay, so for homework assignment for this week, I do have one, but I've not yet posted it online. Okay, it's going to consist of end of chapter problems. I've already prepared it and it's ready to post, but it's on my removable disk back at my apartment, so I can't do it right now. I'll post your homework assignment onto line. It's not particularly long, but it does rehearse end of chapter problems, which is what you need. Okay? And that'll be due the week after Songkran, so you've got 2 weeks. Okay? Okay, have a great Songkran. Bye-bye. There you go. Okay. Oh, one last thing. Just at the end of the break, I posted a bunch of resources that I did have with me, just not your assignment. You can have a look at those that you're interested in. If you're not interested in any, don't look at them. But they go through most of the topics I covered today by either an activity or a short movie. Okay? So, hi.
Selectively remove like ammonia.
Oh well, use boiling point. So the ammonia, hydrogen, nitrogen at room temperature, 2 of them are gases. So while the reaction is carried out at high temperature, take it through a refrigeration unit, the ammonia will condense, come out as a liquid. So you use some physical property.